In the beginning, God created the heaven and the earth. And the earth was without form and void, and darkness was upon the face of the deep. And the Spirit of God moved upon the face of the waters. And God said, "Let there be light." And there was light.
Now, we started radiometric dating last week. I'm going to rehearse a little bit or go over a little bit real quick about radiometric dating. It's used to date the Earth. Supposedly, by looking at the rocks of the Earth and using radiometric dating, we come up with a age of the Earth of about 4.5 to 4.6 billion years. And to a large extent, this has been developed through radiometric dating. And the first thing that we talked about in the class is you have to understand there are certain assumptions that have to be made for it to be true. Now, assumptions have to be made for it to be true. Assumptions have to be made for it not to be true, too. So I'm not saying we got it 100%, that it can't be accurate. Not saying that at all. I'm just saying that for it to be accurate, those assumptions have to be accurate. But for it to be young Earth, it has to be, those assumptions can't be true. And we can't prove it either way. But there's certainly some evidence with carbon dating that we're going to look at tonight that point very much to a young Earth. But I want to make that kind of clear because I might have been a little bit fuzzy last week. And radiometric dating, once again, can only be used to date igneous rock. And igneous rock is not sedimentary rock. It's rock, it's original rock, if you will, that first begins as molten or hot rock, and then it starts to cool, if you want to use that term. And as it starts to cool, that resets the rock, and that sets the date of the rock. That's why when there's a volcano that spews lava into the air, basalt into the air, and you start measuring that, the day it starts doing that is day one. Okay, that's day one for that particular rock. And it's a cooling process that resets it. And as we talked about, all matter in the universe are atoms. The nucleus of atom has protons and neutrons. It's the proton that defines the element, right? The atom, not the neutrons. But if you have an equal amount of protons and neutrons, that's what that element's stable state is. When you have excess neutrons, that's what you have when you'd call that an isotope. And that's what we're looking at in radiometric dating is isotopes. This is the carbon atom, 6 protons, 6 neutrons, 6 electrons. So that's your stable carbon atom, carbon-12. That's what we call it. The weight of the carbon is the number of the neutrons and the protons put together. The atomic number is the number of only protons. I hope I got all that right. But here you got the carbon atom with carbon, carbon-13, carbon-14. Obviously, 13 has 7 neutrons. Carbon-14 has 8 neutrons. These are unstable. They do not stay in the state that they're in, hence the way that we do radiometric dating. They start to change. They use the word decay. That doesn't necessarily imply the loss of protons, and we'll see why in a minute, but it decays into another atom. This is the case of uranium, which is a very radioactive substance that decays eventually into lead. And the thing is, all of these have half-lives. We know how long it takes. We can calculate. We haven't been around 4.5 billion years, as we pointed out last week, but we can calculate what the rate of decay is. How long would it take uranium to decay into that element? Now, you don't use all of uranium, but the radioisotope, the radioactive element changes. When we look at carbon especially, you don't lose carbon, but you lose the isotope. You lose the radioactive isotope. So the carbon's still there. The radioactive isotope is no longer there after 4.7 thousand years in the case of carbon. In the case of uranium and potassium, radioactive potassium, the half-lives are much, much longer. This is the half-life of carbon. So after a certain amount of time, there should be no carbon-14 in anything you found. And that time comes out to be about 103,000 years. So you cannot use carbon-14 dating to date anything more than 103,000 years, because there would be no carbon-14 in that animal, because you start losing it at death, and we'll explain that a little bit later on in the class. So by measuring the amount of daughter element in the rock and knowing the half-life or the decay rate, supposedly the rock can be dated, and you can accomplish this. And there's many of them. There's actually quite a few, but what's used most commonly is uranium, which has an atomic weight of 238, and it will eventually decay into lead, which has an atomic weight of 206. This takes 4.47 billion years. Argon, radioactive argon, decays into, potassium. Potassium decays into argon, which has a little bit shorter half-life, 1.25 billion years. And as you can see there, once again, carbon-14 goes into nitrogen-14. Notice they have the same exact atomic weight. How can that be if it decays? Because it's a different type. Correct. You've read this stuff before. That's right. A neutron has to become a proton. That's a different kind of decay. That's why I don't necessarily just think that decay is loss of protons, because it's not. In the case of carbon-14, carbon-14 actually picks up a proton and becomes nitrogen, which has 7 protons. Carbon only has 6. What happens? Like David said, a neutron had to be changed into a proton in the process of decay. I know it's a little confusing. It might get a little bit easier when we get to carbon in just a minute. I'm trying to go through this pretty hurriedly. And there are again are your half-lives. So the assumptions, initial condition of the rock needs to be known. Most of the time we don't know that initial condition. The amount of the parent or daughter elements in the sample cannot have been altered by any other process other than decay, and we don't know that. And the biggie is the rate of decay has to be constant during this time for this process to work. And there's evidence that it may not have been constant. And again, we use the idea of the hourglass. If you walked into the room, hourglass was half empty, half full, you know that 30 minutes has passed by. And then you walk out later and now the top of it's gone and all the sand's in the bottom, you know that an hour's passed by. By knowing the rate of decay, that's the assumption. And that's kind of the analogy, and it's a good analogy. And then the fourth assumption that John Morris makes in his book Young Earth is that the Earth at least has to be old enough for that decay to be there. It has to be at least old enough for the present amount of radioactive isotope. So does it really work? Is it accurate? And what that means, can we trust it, I guess is a better word to use. Can we trust it? Well, the GREAT group, which we talked about briefly last week, which stands for Radioisotopes in the Age of the Earth. These are young age scientists. They're all PhD degree scientists. Most of them are geologists. There's a physicist in the group, Russell Humphreys, and there's a couple of others, but they came together in 1997 and started using some of their own studies, understanding that old Earth people are never going to do these studies. They're never going to do them. So who's going to do them? Well, somebody. And thankfully, this group got together and decided to do some of these studies, because they've already established that the Earth is 4.7 billion years. That paradigm is never going to leave the old Earth people. And you're not going to win that argument. I get that. But this group did come together and say, well, if this is true, this should be very accurate what we're measuring. Correct? It should be very accurate in what we're measuring. Steve Austin was in that group, and he is a geologist. He's a PhD degree scientist. He's not someone who's just, read the books. He's done the studies, got the credentials to go behind his name to prove it. So he looked at the dating of the rocks that occurred at the eruption of Mount St. Helens. When did that occur? Somebody help me there. 1980. In the 80s. Not billions of years, not millions of years, not even hundreds of years. And what he did was he looked at potassium argon dating, and most of these tests were not done by the rate people themselves. What they do is they take the samples of the rocks and they send them to different labs, reputable labs, not creationist labs, okay? Not people that they've hired to say, this is what number we want you to get. But they send these out to various labs. This is how they do it. And here's what they got with the Mount St. Helens, not telling them where they got the rock, of course. That would kind of be unfair. I mean, that would be cheating, if you will, in my opinion. So what dates did they get for those rocks? 5.5 million to 2.8 million. Not billions, granted, but how old were they? We know exactly how old those rocks were. 20 years, 30 years, whenever they did this study. I don't remember when the study was published. Not 0.5 million, not 500,000, not 2.8 million years. So it destroys the first assumption. You don't know the conditions of that rock when it was first formed. Now this wasn't just done with Mount St. Helens. They did this at other rocks volcano rocks from, and I'm going to mess up that name, but Naruhu in New Zealand, which erupted on 3 different occasions in the fairly recent past, 45, 54, and 75. And when these rocks were sent to 3 separate professional labs, the ages varied from 0.27 million to 3.5 million years old. Again, not billions, but millions. The point is, you can see the problem, can you not? If you know exactly how old those rocks are, and you're getting this kind of age, can you trust the dating process? I would argue you cannot. You know those rocks. We know how old they are. There's not a debate about how old they are. We know when these eruptions occurred. And yet we're getting 2.8 million years when clearly they're not. So that makes me wonder just how accurate those, and I think once again, I mentioned this, I think what they're measuring may be accurate, but they're getting different rock samples from the same eruption. So that first assumption that we have to know the condition of the rocks, we can't know the condition of the rocks. So the scientists tried to do something to take that out of the equation. So they came up with isochron dating. And these were instituted not by creationists, but because they understood there were some discrepancies there. And so they understood that first assumption may be wrong. And they wanted to eliminate that assumption. So they started looking at, the other conditions within the rocks. The problem is, you get the same problem with the isochron dating. Even with isochron dating, wide variations have been found, in some cases as much as 500 million years. I would submit that's a long time. I would submit that's a long time and a long variation on rocks that shouldn't be there. And they looked at the Cardenas basalt, considered to be the oldest strata in eastern Grand Canyon. The rate group did this. And that's just a diagram, not too clear, but where they took their samples from the Cardenas basalt. So what explanations can be given for the discordance of age? So there's got to be some explanation, right? By our scientists? Well, there could be mixing of isotopes between volcanic flow, but this can be eliminated by determining whether such mixing occurred, which can be easily done. Throw that out. That doesn't work. It's possible that the minerals could have solidified at different times, but there's no evidence that lava cools and solidifies in the same place at incredibly slow places at different times. Thus, this cause of discordance can be eliminated. Doesn't work. So the most likely explanation for the discordance is that the decay rates may have been different in the past than they are today. An explanation that most scientists just quite frankly are unwilling to accept. They're uniformitarians. They're not going to accept that. So much of the work done by the rate group has been providing evidence that radioactive decay actually supports a young Earth, and that the decay rates in the past must have been different than they are today. One example. This is not my field of expertise. You guys know that. But I've done study on this, and I don't purport to be a geologist or expert in radiometric dating, but I've done the best I can. I'm a physician. I know more about biology than I do this stuff. But these are things that the rate group have come up with. An example can be found in helium found in granite in the form of zychron crystals, which contain radioactive uranium decaying into lead. That's what we've been talking about, right? And so they look at these zychron crystals that occurs after this decay takes place. So during this decay, 8 helium atoms are formed in micron out of the zychron and granite rapidly. The helium in the zychron crystal should have migrated out by our present time, but we still find it. Given the age of that rock, we shouldn't be finding the helium in these zychron crystals, but they're still there. We see lots of helium, as a matter of fact. It doesn't jive with the paradigm. Why so much helium? Decay rates at one time were greatly accelerated. In other words, helium was being produced faster than it could escape, thus leaving lots of helium still in the rocks. Different decay rates would explain it. But taking the old uniformitarian group point of view does not. So based on the measured helium retention, statistical analysis gives an estimated age of the zychrons at 6,000 years plus or minus 2,000 years. That fits a lot more with the young Earth position, doesn't it? This agrees with the literal biblical history and is about 250,000 times shorter than the conventional age of 1.5 years for zycrons. The conclusion is that helium diffusion data strongly supports the young Earth view of history. Another discovery. Again, I know I'm going through these rapidly, but We need to finish the course here. Another discovery indicating decay rates were different in the past is that polonium halos that are found in granite rocks as well. Remember, granite rock is igneous rock, the rock that you use to date things. Polonium isotopes producing halos in granite rocks are daughter products, once again, of uranium isotope to lead, the half-life of being 4.47 billion. That's a picture of a halo. You can look at these things under microscopes. Polonium, on the other hand, in its isotopic form of 210, 214, 218, only has a half-life of 138 days, 3.1 days, and even 0.00016 seconds. Would you expect to find any polonium in that granite if that's what their half-lives are? And the rock is, let's just pick a number, a billion years old? No. But by looking at biotite crystals containing halos in the granite, no uranium is found in them, so polonium must have been in the biotite as the granite rock cooled. The presence of polonium halos in the biotite crystals means that the time between the embedding of the polonium and the formation of these crystals had to be less than the youngest half-life of the enclosed polonium isotope, 138 days. So the changes occurred very rapidly. Polonium halos could not possibly have formed because all the polonium would have decayed sooner after it was synthesized. And if these results are correct, this is according to R.V. Gentry, who is a geologist. He's not part of the rate group, and he's the one that's done these studies on polonium halos. If these results are correct, then the fundamental postulate of modern geochronology, i.e., the assumption of the uniform radioactive decay rate, is called into question. And indeed, the entire framework of modern geology is open to reinterpretation using different premises. Another bit of evidence is fission tracks. Fission tracks are produced also by this radioactive decay that's going on. Unstable atoms such as uranium into smaller atoms like palladium. The rate team wished to determine if the fission tracks density, thus the fission tracks ages, matched the quantities of nuclear decay measured as the radioisotope age of the same rock. What did they find? I think you figured it out by now. They find that in fact it did not. For example, the discordance between 75 million versus 169 million years was found in the rocks of the Cambrian geologic formations. Big discordance. It's a big difference. 75 to 169, big discordance. Further discordance was found in rocks measured in the Upper Jurassic system, with rates ranging from 88 million years for the youngest rock to 1,036 million years, plus or minus 310. That's still a big difference, whether it's the minus 310 or not. That's a huge difference. So there's a discordance. So what we're saying is the accuracy is in question, and the decay rates could very well be the issue. It doesn't prove a young Earth necessarily. I'm not saying that. But I'm saying that there's some discrepancies there, and it's not solid. And yet, what do you do? What do you go to, or if you go to any textbook in the country, probably in biology? I know in the Texas textbook, I know because I've read that textbook, and they just look at radiometric isotope measuring as stone cold solid, no questions about it at all. And we're trying to poke holes in it, and the rate team has done that. The fission. This is from Hodges in his book. The fission track density agreed with the excessive helium retained in the rocks, which we've already studied, embedded in Pre-Cambrian granodiorite, and with the abundance of parentless polonium halos, along with uranium halos preserved in the granite masses and coolified wood as evidence for an accelerated nuclear decay. So how do geologists deal with the evidence for young Earth? You think they worry about it, first of all? No, they don't worry about it. But if you presented it to them, well, this is it. Scientists have physically ruled out a young Earth. This was from study one when you talked about evolution, right? Their paradigm is there. They've ruled it out. It can't be. So they're not going to. So if they see this, any evidence to the contrary are either given as ad hoc explanations or considered to be isolated anomalies which do not fit in the world paradigm of an old age. They slough it off. So that's why I say the rate team. And the rate team, as far as I know, is still active. They're still out there doing what research they can. And consider they're not being funded by untold millions of dollars from the United States government. That's not happening. They're somewhat limited in what they can do. So the evidence mentioned thus far should not, and this is from John Morris. I don't know if his name shows up there or not, but this is a quote from him. The evidence mentioned thus far should not leave the impression that radioisotope dating has been overturned. And here's the quote. As John Morris says, it has been called into question, flaws in its foundation exposed, and its results shown to be inconsistent. In short, it is in trouble, but it's still a very formidable concept in the minds of many. Don't think we've overturned it by this, but we've shot some holes in it. Let's look at carbon-14 dating. Carbon-14 dating, the dating process. I'm going to try to explain this the best I can, the simplest. This is schematic. We won't go through all this of what happens. But consider this. Carbon exists in at least three forms. Carbon-12, by far the more common, and I messed this up last week when I gave the ratio. There's much more carbon-12 than there is 14, like 1 trillion times more. I think I said it the other way around, but I just messed it up. So it's the more common form in the non-radioisotopic form. It's not going to decay. You leave it sitting around, it's not going to decay. It's only and I want to make that clear because I don't think I did last week, it's the radioactive isotopes that decay. That's what you're measuring. So you're going to have carbon around. You're not going to run out of carbon. It doesn't decay to zero. It doesn't do that. But its isotope does. And there's two isotopes that we know of, and we have carbon-13, carbon-14 exist. And the most unstable of all this is carbon-14, which, as you can figure, since carbon has 6 protons, it has 8 neutrons. And that's just a picture, give you a picture. And carbon-14 is less than 0.1%. It's even a lot less than that. You do the math, trillion to 1, I don't know, it's a lot less than 0.1%. Carbon-14 is radioactive. It is unstable by nature. And it will decay through beta decay. That's a different kind of decay than alpha decay. That's why it's different, like David pointed out. Beta decay, where a neutron of carbon-14 is converted into a proton, thus changing it into nitrogen. Becomes a totally different chemical in its decay process, which has an atomic weight of 14. Nitrogen then is a stable molecule. 7 protons, 7 neutrons. That's what you're looking at. Now, carbon-14 then combines with oxygen to become carbon dioxide, which gets incorporated into plants, animals, and all living things. Thus, all living things contain the same ratio of carbon-14 to carbon-12, and it's in the air that we breathe. Basically, we all have about the same ratio of carbon-12 to carbon-14 in our bodies while we're living. While we're breathing, that ratio remains the same, whether it be animals or plants. That ratio is basically in all life. That ratio is the same as long as you're breathing and you're eating and you're taking in nutrients and so forth. That ratio doesn't change. What happens when you die? You start losing. That's when the decay process starts. Like in the analogy of the rock when it starts cooling. The clock starts on carbon dating when you die, or when any animal dies. That's when, because you're not breathing in the carbon-14 anymore. You know, you're not breathing anything in. So a key thing to remember, as long as an organism is alive, it will contain that same ratio of carbon-14 and carbon-12. And that ratio, once again, carbon-14 atom to every 1 trillion carbon-12 atoms. So it's 12 trillion to 1. That ain't much, but that's enough to be measured. You can measure that. And at death, this ratio will begin to change as the carbon-14 atom is unstable, and thus the smaller ratio, the longer the atom, the organism has been dead. So if you know what that ratio is, and you start, and that graph we saw earlier shows that, if you know what that ratio is, and that ratio starts declining, knowing the half-life of carbon, you can figure out how long that animal has been dead, correct? And how long is the half-life of carbon-14? Thank you, 5,730 years. So it's not very long. So if someone says, I got a dinosaur here that's 1 million years old, they ain't used carbon-14 to date that. They've deduced it some other way, because carbon-14 would not be around, should not be around, if all this is accurate. So since the half-life of carbon is relatively short, 5,730 years, used to date fossils, that you really, after you get past about 50 or 60,000, it can go up to 100, but it's really not very good for that because there's hardly anything around by then. That's all it can be used for. So carbon-14 dating, just as isotopic radio dating, must also assume those same things that we talked about. The assumption must be given to how fast carbon-14 decays, and how fast carbon-14 decay has been in the past, and what was the starting point of carbon-14 in the organism when it died. And even the more critical assumption is the ratio of carbon-14 and carbon-12 in the atmosphere. That's a big assumption. We know what the carbon-14, carbon-12 ratio is in the atmosphere is now, but what was it 5,000 years ago? Ratio could have been quite different than it is now, and that would have made a big difference in how you use the dating. Has it always been the same? It has to for this to be valid. In the New Answers book edited by Kenham, Mike Riddle states that the founder of carbon-14 dating method, Dr. Willard Libby, assumed this ratio was constant. So he assumed that the amount of carbon-14 and carbon-12 in the atmosphere has always been the same. His data didn't point out that, and his reasoning was based on an evolutionary concept. Libby's original work showed that the atmosphere did not appear to be at equilibrium in the past, and that the Earth started, and that if the Earth started with no carbon-14 in the atmosphere, let's say there was no carbon-14 in the atmosphere, how old could the Earth possibly be if that was true? The maximum age the Earth would be 30,000 years if there was no carbon in the atmosphere. And it appears not to be at equilibrium. I wasn't around 30,000 years ago. I don't know if the Earth is 30,000 years, but none of us are there. We can't measure something that was 30,000 years ago. So Dr. Libby chose to ignore that discrepancy, not the non-equilibrium state, because it didn't fit with the evolutionary paradigm. And he was the one that discovered it. He ignored it, and he attributed it to experimental error. So if you can't explain it, it had to be an error. However, this discrepancy turns out to be very real. That ratio does not seem to be at equilibrium. The rate of carbon-14 and carbon-12 is not constant. Obviously then, if the carbon-14 is still not at equilibrium, the Earth must be very young. If we're still trying to reach equilibrium, we haven't even reached it yet. Other factors that affect the production of carbon-14 include the magnetic field. So if the magnetic field was different, there would be less carbon-14 in the atmosphere. We know the magnetic field is changing. Scientists tell us that. And that probably was quite different 10,000 years ago than it is now. The flood recording in Genesis may have also played a factor in the amount of carbon available for that. So when the flood is taken into account, along with the decay of the magnetic field, it is reasonable to believe that the assumption of equilibrium is a false assumption. That's from Riddle. So the rate group demonstrated results of carbon-14 dating that had serious problems for long geologic ages. To me, I may be missing something again. This is not my field of expertise, but this seems so obvious to me. What's the explanation? Maybe somebody can tell me that. I don't know. I need to do more study possibly, but to me it just seems so obvious. For example, they took samples of 10 different coal layers representing different periods of geologic column that were dated millions to hundreds of millions of years old by standard evolutionary estimates, and found all samples contained carbon-14. What did we just say about carbon-14? What's the half-life of it? At most, would there be any around after 100,000 years? So how can those coal deposits have carbon-14 in them? I'm missing something. If they are, in fact, millions of years old. Well, they're not millions of years old. That's what we're saying here. Why is that significant? Again, half-life of carbon-14 is relatively short, and one would expect no detectable carbon-14 after 100,000 years, and yet they're supposed to be millions of years old. And these were sent to different labs. Carbon-14 was detectable. How about diamonds? How old are diamonds? We're told that diamonds are millions of years old. That's what I've been told. They take millions of years to form. Would you expect to find any carbon-14 in a diamond if it's millions of years old, based upon the science that we just talked about? The answer is no. Well, you can guess it. Diamonds are believed to be millions and millions, if not billions of years old, and clearly should contain no carbon-14. However, as you might have guessed, carbon-14 was indeed found in 12 different diamond samples tested by the rate group. The conclusion is carbon-14 can never be used to date objects more than 100,000 years old, and when you find them in objects, that object should not be more than 100,000 years old. Now that's older than what we believe the Earth is as young Earth creationists, but it is a lot younger than the old Earth creationists, or the old Earth people believe, isn't it? 4.7 billion? So, any questions on that? Did I make that as fuzzy as I possibly could? Okay, so in conclusion, all radiometric dating methods are based upon assumptions of what occurred in the past, which basically cannot really be proven. We have to look at the evidence. But when these assumptions, which are all biased towards an old Earth, are removed, if you take that rate of decay especially out, and shown to be faulty, which we have shown there's a lot of discordance, the results then support a biblical young Earth. And no, we don't have to be, especially carbon-14, we don't have to be afraid of radiometric dating methods, and especially, like I say, in the case of carbon-14, because in my view, it actually proves a young Earth if you take those assumptions away.